So, yeah, as Timani mentioned, the topic of this talk is was the same as the topic for my master's dissertation, which I recently completed. So, yeah, I'm going to talk a bit about deep generative models for high-energy physics simulations. Yeah, and it was quite a nice project to dig your hands into and really get to explore data in a very the nucleus. But we've actually discovered that even the protons and neutrons themselves have actually a substructure, which is essentially composed of quarks and gluons. So you've also got something called color charge here, which needs to be balanced for these hadrons to be able to exist. So you've got, if you think about colors, you've got blue, green, and red, and if you combine all of those together, all the primary colors, you actually get white. And that's sort of it's not really like they have colors, it's more just a way of understanding the charge that has three components, the three different levels. But essentially, a proton then consists of two up quarks and a down quark, and there's both electrical charge and color charge that goes into this equation. To get a charge of positive 1, the charge of the electron, you actually have these two up quarks with a combined charge of 4/3, and then you subtract 1/3 with this down quark, and then you get a +1. And similarly for a neutron, the charge balance is then 0. Yeah, and then you've got other kinds of hadrons which actually only have two quarks, and in that case you'd have like a red and an anti-red, which would also give you a balance of 0. Yeah, and then you've got the God particle, which is essentially a manifestation of the Higgs field. So all particles are embedded in this Higgs field, and by interacting with that field, they get their distinguishing masses. So without that, all particles constantly move at the speed of light, which you can imagine what that would entail for the structural integrity of the universe. Like everything would just, nothing would actually be structured. Yeah, and then you've got these force-carrying particles. The photons, the well-known one for the electromagnetic force, and gluons are what actually helps the strong force keep these quarks within the confined boundaries of hadrons. Cool. So the Large Hadron Collider is this massive structure under the Franco-Swiss border. It's mostly under France. And you've got the Alps there in the background. It's a massive structure, 27.1 kilometers in circumference, and it's about 100 meters underground. And it also actually slopes a bit to avoid the mountainous structure that makes it so around it. So what people don't generally know is that actually the LHC is the last set in a set of successive accelerators which take particles to increasing energies as they move along these accelerators and eventually get released into the LHC in two different directions, where they are focused by dipole magnets to actually collide at these four main experimental sets. So CMS, Atlas, Alice, and LHCb. Cool, and it's really crazy when you think about what's actually happening here. So these particles travel at basically the speed of light. So it means that during an LHC run, which takes about 10 hours, a particle can travel around the LHC ring for a total of 10 billion kilometers, so 11,000 revolutions, 11,000 times around that entire LHC ring per second. And that's about, in a 10-hour run, the distance to Neptune and back. And so the total energy of these particles are equivalent to each of those proton beams is equivalent to around a 400-ton train traveling at 150 kilometers an hour in each direction. And that results in about 1 billion collisions per second and generates about 50,000 terabytes of collision data per year. This is just some photos that I took at CERN. So this was at 11 o'clock at night, so you can imagine how late you can work there. Just a little car with AI in the number plate, which I thought was pretty cool. Cool. And then the Alice collaboration focuses mainly on the Big Bang. So when you look at the Big Bang, the evolution of the history of the universe goes through quark-gluon plasma phase to where protons and neutrons are produced. The nuclei only happened around 3 minutes after the Big Bang, and the Earth was only formed around 4.5 billion years after the Big Bang, and currently we're sitting at around 13.7 billion years ago. So I just want to everyone mutes their mics, please. Hearing some feedback there. Cool. So at the LHC and at the relativistic heavy ion collider in America, these are the only two colliders that currently can reproduce where we have a deconfined state of matter where these quarks be deconfined and they're no longer contained within these color neutral hadrons. And that's because of either, so you can form that either by increasing the density or the temperature of the but it's mainly achieved by increasing the temperature to like millions of times the temperature of the core of the sun. So it's an extremely high energy collisions. And essentially what they do there is they collide. These are two lead ions, so you can either collide two protons or two lead ions, and they don't always collide head-on. But when they do collide, they actually form this minuscule representation, the space-time domain of the core gluon plasma, and out of that collision comes this whole mess of decay products. So these particles like kind of branch and form various decay products, which have other branches, and that's all detected by these massive detectors, of which ALICE is one. So if you look at the 3D like kind of representation of this collision, you can see that the way that the tracks bend kind of give you an indication of the momentum they're traveling at and the direction in which they then give you an indication of their charge. And these bars over here just like indicate the energy deposit at that specific point. And then this further I took outside the ALICE experiment. So this is almost to size. It's a bit smaller, but you can see that like the scale of a human, this is a massive detector. You also have to go down a lift to minus 51 meters on the ground to actually get there. And yeah, so I actually got to see this structure. It's just stared at it for like 20 minutes when I saw it. It's crazy. It's like a massive camera, like a massive microscope. Structure around it is actually the magnet. It's like a solenoid that this entire detector is embedded in, which allows the particles to bend so that it can be studied easier. Cool, and so the detector is actually a multi-layered structure. So each of these detectors are actually studied by a different group, or a different group takes responsibility for them. So the transition radiation detector is located here. It's a multi-layered detector in its own right. But yeah, so all of these sub-detectors actually inform the entire reconstruction of the event. So some of them are involved in actually finding the central point of the collision. Others are more concerned with tracking, like where did that particle actually go. Others are concerned with energy deposit and studying various types of particles. So the transition radiation radiation detector itself is composed of multiple modules. So you've got 18 modules in phi direction, so around the azimuth, and then you've got 5 modules along your z-axis. So this is the direction of the beamline where the particles actually collide. And then going outwards, you've got essentially each of these modules has six layers. So this is important because each of these independent layers gives you an independent measurement for each particle. And that's useful for Bayesian approaches when you actually want to do particle identification. Going a bit deeper into the actual structure of these modules, you get these multi-chip modules at the end, which essentially is where the detection actually happens. So each of these has a radiator, which is something similar to polystyrene. And essentially when certain particles like electrons traverse across this radiator, they emit something called transition radiation. So a big job of the transition radiation detector is actually to distinguish between electrons and pions. And when electrons pass again across this boundary, they actually emit transition radiation and pions don't. But both of them actually, so there's a little gas chamber here. Just ignore the plot. So just imagine that this area here contains xenon CO2, which is a type of gas. And as these particles rip through the gas, they actually rip off electrons and ionize those gas particles. And the gas particles then migrate because there's a charged anode wire and a cathode pad over here. So the charged particles actually migrate towards the anode wire and essentially get absorbed on this cathode plane over here. And the structure of the data is then essentially a two-dimensional distribution, so along pair dimension and along time dimension. So the time bins are basically just subsamples of a defined time interval at which these charged particles, the gas molecules, actually arrive at the cathode pad. And then the height of this would be the amount of charge that is absorbed at that time point. And the pad dimension is just essentially where the particle passed through. So it's quite useful to have a blurry image because that gives you a better way of averaging the actual spatial dimension. So you don't actually want it to be too crisp. You actually want that that blurriness so that you can more accurately distinguish where the part actually went through. And this is these are some photos that I took at the actual run control center. This was not during a run. Obviously wouldn't be allowed in there. But yeah, so there's all these like graphs and things to actually during a run monitor what's happening. You can see that if a detector layer is off or if something critical happens, then they can maybe pump the beam or restart. You obviously don't want to restart, but if enough of the detectors are not on, you might want to do that. Cool. So that's enough physics. So I'll get into the actual what I did for my thesis. So this is basically just the data extraction process. So this is my local machine, and essentially there are two main servers that I worked with: the HEPA-1 server at the physics department at UCT, and then the high performance cluster, which is just the general UCT cluster for that gives you access to like GPUs and things if you want to do hectic parallel computing. And yeah, so essentially I had the script which interacted with the worldwide LHC computing grid and essentially submits jobs to this and then extracts the data for the specific runs that I want. And then I download that with a makefile onto the server, and then from there go back and SAP or async it back onto my local machine. And then from there you can basically do your backups onto repositories, and essentially if you want to work with a high performance computing cluster, you can just clone your repositories onto there and then run your scripts from there. So quite an involved data processing architecture. And yeah, so not only did I get to work with this computer grid, but I actually got to see it in real life. So it's quite a high temperature in this room because Switzerland doesn't really like allowing people to use air conditioning because of the energy consumption. But yeah, so yeah, massive structure. This red area over here is the largest internet backbone in Europe as well, also contained within that data center. Cool, so the actual data consists of electrons and pions, and we've got a very large class imbalance. So you can see that we've got about 90% pions and 10% electrons. And essentially it resulted in about 19.7 gigabytes. The runs that I used came from 2016. And then, so basically the data structure I'll show in a bit, but there's also some metadata about the angular coordinates, eta, theta, and phi. And then the specific detector element that the particle passed through, some info from other detectors and so on. And then there was quite a bit of missing data as well. So even in such a precision way that malfunctions. So often you have detector elements that are off, or you can find that your tracking was incorrect. So you actually miss the particle and you just obtain an empty signal for that particle at that coordinate. But yeah, so essentially the data looks like this. So for each particle you have these 6 signals, 6 independent measurements, which are, as I mentioned, you've got your space dimension here. So we basically took a very wide window to ensure that we actually obtained the particle that we were interested in. And then we've got our time bin samples along this axis. So you can imagine that this is the peak. If you integrate over this time bin, you actually find the total charge deposited at that time bin, at that point in space. And yeah, essentially this information is quite useful if you want to do particle identification using a Bayesian approach. It's not really useful if you want to combine it as a single tensor with 6 channels. I tried that, it didn't work well at all, but if you use a Bayesian approach, it actually works quite well. And another way to actually look at this data, so you can look at it as an image, so 2D image, or you can look at it as a time series. So you've got this total charge deposit, which is that integral, and then you've got your time bin over here, your time series along this time axis. And in that case, you can actually see that there are some differences between the signals, the average signals obtained for electrons and pions. So on average, the electron charge deposit is quite high, and it's got this additional peak here at around 2.5 microseconds, which is the transition radiation that an electron emits and that a pion doesn't. But obviously, as we all know, an average is not really a good measure of everything, so you need to look at the distribution of your data, and if you look at that, then you can see that there's these red lines are actual individual particles and the black lines are averages for electrons and the blue lines for pions. So you can see that there's quite a bit of variation around that mean, but the average does hold. You do see that the electron signal is higher, and you do see this additional peak that is the transition radiation. Cool. So now for the cool data science stuff. I use deep generative, or you can also call them latent variable models, to actually try and model to simulate detector response functions. So why would we want to do this? So why do we want to simulate this data? Because, I mean, we obviously have a lot of data already, as I mentioned. But essentially, computer simulations give us a theoretical reference for the measurements that we perform at the LHC. And then we can compare our models against the actual physics that is measured during a run. So if we look at the discrepancies between the simulation and the data, we then look for any signs of disagreement between the simulation and the actual data. So that's essentially a disagreement between the theory and the physical universe. And that could lead us to discover new phenomena. It could actually lead to adjustments of the standard model. And we could actually discover new fundamental principles of nature. And even if we don't find anything spectacular, we can still refine our models and refine our simulations so that we can better understand the physical laws behind them. So what's currently used for simulation is GAN. It's as I mentioned, it's the C++ software infrastructure that is involved in simulating data, and it's based on Monte Carlo principles. It's a huge set of software, so it actually simulates everything that happens during an actual LHC run. So you've actually got the materials, you've got the geometry of your detectors and the different particles that interact with that detector geometry. You model the tracks and how they interact with the detector to get the hits, and all that, all the way through to interacting with the same software that is used during an actual run. So you simulate and you then detect using the same software that you use during an LHC run. So basically, to be able to motivate not using this, you need to first show that it's not 100% reliable. So I built a convolutional neural network with this structure over here. So just 2 convolutional layers and then 3 dense layers, and essentially was able to distinguish between GAN simulated and real data quite reliably. There is this, so this distribution over here is the prediction of the classifying neural network's probability that this particle is real. So if it's obviously 1, then it's very certain that this is real data. If it's 0, then it's 100% certain that this is simulated data. So basically, we are able to distinguish these two quite well. There is this one peak at around 25% probability where the network is a bit confused, and when we actually plot the particles that result in those probabilities. So to understand this diagram, I'm going to use the same diagram, the simulating processes as well. We essentially have these images which range from high probability of being real to very low probability of being real. So you've got your 90s and your 80s up here, and then you've got your 70s, 50s down here. So images that received like a 25% probability, only those empty images where we actually didn't obtain data, or we missed the actual particle because the particle might have just hit a nut or a bolt or something and just deflected completely, and we just missed it entirely. So you can see that GAN actually models the distribution of the amount of empty images that you expect quite well. So that's because that's this peak over here where GAN is just slightly more than that seen in real data. So then I basically looked at how can we actually one day replace the Monte Carlo simulating processes by latent variable models. So latent variable models or deep generative models rely on this concept of a latent space, which is similar to, you can almost think of it as PCA, but PCA is not a very good representation of this latent space. It's just to give you kind of an idea of what it is. But essentially what you do in your latent variable models is that you want to map from your data space, which can lie along any kind of manifold. You want to map through neural networks to get to this latent space representation of your data, which is sort of like a compressed version of your data with the major factors of variations accounted for. And then you want to sample from this latent space. You pass that through a functional approximator, which is normally also a neural network, and you then map back to your data space. Using the kind of infrastructure, you actually capture the true data distribution along a much reduced amount of latent variables. So if you think about your data space, it's like composed of like 1,000 variables, you can then map that to 2 or 3 or 5 latent variables, which are the main factors of variation, and it kind of tries to not model the noise too much. So again, why would we want to do that? Why would we want to replace the current simulation software? It's mainly because of compute. So currently most of the LHC computing grid CPU budget is dedicated towards simulation. So if you think about CPU years, they spend about 500,000 CPU years per year just simulating experiments. And latent variable models are around 100 times faster than Monte Carlo. So at the moment, Monte Carlo works, but the LHC is currently in a phase of upgrade, which will increase the luminosity factor, which is basically the amount of particles that are produced per cubic centimeter or per square centimeter per second. So that will go up to around 1,000, which is 10 times more particles per unit area per second, which is it's massive, right? So they've got to find faster ways to actually do these simulations. Cool. So now that I've given the motivation, I'll talk a bit about the models themselves. So generative models are concerned with modeling high-dimensional distributions and dependencies between those random variables. So we actually want to be able to generate data that is similar to the data that we were training on, but not exactly the same. So if you think about the training examples, they're distributed according to some unknown distribution, P of x, and we want to model a distribution which is similar to this that will allow us to generate new examples by sampling from this model distribution. And obviously, if you want to use a function approximator, a neural network is a good idea. So essentially, as I mentioned, these deep generative models usually make use of a latent space representation of the input data. So to understand the latent space a bit better, there's this image over here that might explain it a bit in more detail. So if you've got your training data and imagine that they are images, you essentially want to find a neural network which can map from this image to a specific space in this plane or specific area within this latent space. And for each image, find a specific place in the latent space that that image maps to, which will then allow you to sample from this latent space and regenerate as similar as possible to the image that the neural network has seen before. So the latent space is something that is a continuous space, and if you move around in that latent space, you can actually find that certain, not necessarily variables that a human would think of the images as, are captured inside this latent space. So these are images of that the child drew of like plants and like trees and flowers and things. And you can see that if you move in certain areas of this latent space, you'll move more towards, like, let's say, a green color channel, more towards trees. If you move in, let's say, this direction, you move more towards flowers. So it's kind of an abstract way of understanding it, but it turns out to be quite useful. Similarly here, some kid drew, different children drew owls. So you can see that if you move around in this latent space, it's sort of like a continuous change that you get as you move towards this space. You maybe get like an owl which doesn't really have a body, whereas if you move this space, it's got more of a body and a smaller head. And then you also get basically like this basic arithmetic within the latent space where you can do some interesting things like taking the latent vector for a smiling woman and subtracting the latent vector for a neutral woman, adding a neutral man, and then getting a smiling man. So this is useful to think about how the simulation process actually works. Like, how do you actually arrive at your final input, your final output, given all of these latent factors that are inherent in your data. Cool. So when there are complex dependencies in the variables in your input data, these generative models become very hard to train. So essentially we want to draw samples from a latent distribution constructed during training. So we actually have this encoding network that gives you the latent space, and then before we start generating back from that latent space, we actually want to sample from the latent space first. So basically the model samples from the latent space and then generates a new image. So in order to actually deduce that your generative model is representative of the underlying data distribution which you're trying to capture, you need to find that for each data point X, there are one or more latent variable settings which actually result in the model generating something sufficiently similar to the X that you gave it. So essentially, you're sampling latent variables from this high-dimensional space Z according to a PDF, which is defined over a group of deterministic functions, and these functions are neural networks parameterized by theta. Essentially, with a neural network acting on your latent space parameterized by theta, you're hoping to map back to X, to your actual data distribution. So after training, this function will be deterministic, and then you'll randomly sample from Z. Obviously, the parameters of your network is fixed after training, and then this neural network, which is conditional upon Z, is actually random variable in your data space. So you want to optimize your hyperparameters or your parameters so that when you sample from Z, you'll have a very high likelihood of outputting something similar to your training data. Also, more formally, we actually want to maximize the probability of the data over this integral. So overall X, overall Z, we actually want to maximize the probability of X. So that's basically the f of Z of theta that we basically explained in the previous slide is here just defined as a distribution where X depends on Z. And maximum likelihood then underpins the notion that if X is likely to be reproduced by this process, then we're also likely to generate similar examples that are similar or from the same data distribution as X. And often this latent space is modeled as a Gaussian or a multidimensional Gaussian. So essentially, the distribution, we're trying to find the mean of this distribution, and we're trying to find the standard deviation of the distribution, which is multiplied by the identity matrix. In general, we'll not find that, so most Z will not result in anything similar to X, but we can actually maximize the probability of obtaining X via gradient descent by making this function approach X, given some latent variable Z. Cool. So in practice, the most beautiful thing for me about the latent variables is actually the variational autoencoder. It's an extremely beautiful idea to me. But essentially what you've got is you've got input data, and you've got a neural network, which is an encoder, the mean and the standard deviation of the distribution of these latent variables. So each latent variable has its own distribution, so it's not fixed. And essentially, you then take these variables and you basically map them through a decoder to try and reconstruct your actual input image. So you've got two parts to your loss function. You actually have this reconstruction loss, which is just the mean squared error between your original input image and the reconstructed version. And then you've got this KL divergence loss, which you're basically trying to make your latent variables as close as possible to the standard normal distribution. So in general, I mean, you can define this distribution to be anything you want, but a normal distribution is just a reasonable assumption because of the central limit theorem and because it's quite easy to actually compute the KL divergence of a Gaussian compared to some other distributions. Cool. So yeah, to give it a bit more of a visual aspect, you can think about MNIST. So most people are used to being introduced to topics in MNIST. So if you take MNIST, which is basically a set of handwritten digits, you basically map that through this encoding neural network over here to this latent space. And here we're just looking at a latent space with two variables. So you've got like latent space variable number 1 and latent space variable number 2 over here. Then you can find a place where these digits actually map to in that latent space. So you can see that the purple area is where your 0 is mapped to, and the blue areas where ones map to, so that would be somewhere over there or there. And then essentially you can actually like linearly interpolate it within this latent space to find out where certain digits would be sampled from. So you'll find that like your zeros are sampled from here, and as you move upwards, you find something like a 6. So it's just useful for the neural network to know that, okay, a 6 is similar to a 0, but it's got this extra little thing over there, that extra line over there. And as you move maybe towards this side, you get something like a 2, or if you move downwards from a 0, you can find a 1. So it's quite interesting to see how this how the neural networks actually find a useful representation of this training data set to reproduce something very similar, but mostly unseen. So you can generate a new 3 that it's never seen before, or a 9 that it's never seen before. Cool. So a bit more detail about this. So in a VAE, your Z is from the standard normal distribution, and essentially the f of z of theta is a set of neural networks where the initial encoding neural network will be involved in generating the Z variable, and the later decoding network will be tasked with mapping from the Z back to X hat, which is trying to be as similar as possible to X. So we're trying to maximize the probability of P of X, but trying to find a computable formula for it. And then obviously we do stochastic gradient descent to optimize the parameters of that neural network. For most P of X, or for most Z, P of X will be close to 0. But for the VAE to be useful, we need to sample Z values that are likely to actually result in a sample from our true data distribution. So we define this function Q of Z conditioned upon X. So that's essentially, this Q of Z conditioned upon X is actually the encoding network. So it's trying to take this existing X value and then calculate a distribution of Z values that could have realistically resulted in X being generated by the decoding network. So we're trying to narrow the universe of possible latent variables down from the large universe of all Z's likely under the prior. So this is the central formula of the VAE. So basically we want to maximize the variational lower bound, but essentially by doing that we're trying to maximize the probability of X, and we're also trying to minimize the KL divergence between the Z variables and the standard distribution. But this is not, so P of Z of X is, given X is not analytically solvable. So it simply describes Z values likely to reproduce X. But the second term on the left is forcing Q of Z of X to be as similar as possible to P of Z given X. And on a model with sufficient capacity, it should be able to be exactly the same with P of Z of X given X. So once we've actually minimized this KL divergence term, we can then start maximizing this probability directly. And that makes P of Z given X tractable. So we can actually, in practice, we actually use this formula on the right. So this is actually differentiable, and that can be optimized using gradient descent. So to understand the formula, we basically have Q, which encodes X into Z. So we have this distribution of Z given X, and then we have P, which then takes this Z variable and reproduces X. So this is again Q, and this is Z. Sorry, Q and P. Cool. So in practice, so in theory, we basically want to sample from this normal distribution during training, but obviously you can't perform stochastic gradient descent on a sampling process. So it's impossible to find the gradient of a sampling process. So what you actually do is you basically just want to find your mean and your standard deviation using your encoding. You want to do is you want to sample from the standard normal distribution. You multiply by your standard deviation, add your mean, and then you've got the same thing that you were trying to do here. And then you can feed that into your decoding network, and then you've got your two loss terms over here. So you've basically got your reconstruction loss, which is the difference between your actual X and the regenerated X. And then you've got this KL divergence loss term, which is how similar your modeled latent distribution is actually to the standard normal distribution. Cool. So in practice, for the reconstruction loss, I opted not to use mean squared error, and I'll get into why I did that. But I'm just quickly going to introduce this customized loss function which is called focal loss. So if you think about your normal binary cross-entropy loss function, you've got quite a smooth function as your data, if your data was, your true outcome variables was 1. As you approach 1, you've got a very smooth descent in this loss function. But we actually, so if you want to model that, if you want to express that mathematically, you're going to find this variable pt, which is y hat if the true value is 1, and 1 minus y hat if the true value is 0. And then your binary cross-entropy loss function is just minus log of that variable here instead of this much longer formula over here. But then what focal loss basically does is it's got this weighting parameter gamma, which essentially downweights the contribution of your well-classified examples to your overall loss function. So you can see that you can choose a specific gamma, like normally they use a gamma of equal to 2. So then you can get this much much lower contribution to the loss function once you start getting closer to your actual what you want the outcome to be. So if your true class is 1, as you get close to 1, so above 0.5, the contribution to the loss function actually contributes less. So basically, the reason I did this was when I trained VAEs using mean squared error as the reconstruction loss function, you get these very blurry images, which is generally the issue with variational autoencoders, that they generate very blurry images. And in contrast, if I used focal loss from the start, then I actually got very high loss at the beginning, so the neural network struggled to find traction. And I actually found that the images that it produced were sort of like inverted from what I expected. I'm not 100% sure why that is. But basically, when I played around a lot with these things, and essentially what I did with the most successful one was that I did a 2-step training process. So I actually pre-trained the neural networks where I scaled the images to have a pixel range in -1 and 1. And then I used like a tan-H activation function in the final layer to actually map to between -1 and 1. And then I just trained for 2 epochs at a very high learning rate so that I could just get the weights in sort of like the right ballpark. And then after I did that, I then rescaled the images to be between 0 and 1 so that I could use the focal loss function. And then essentially use the same weights. So just saved those weights and then loaded them into the same neural network where then I have to go like sigmoid, so between 0 and 1. And then I trained I reduced the learning rate to like 10 to the -8 so that we could gradually now find the right space of the hyperparameters to actually be in the right setup. And yeah, so basically, even though there's some crazy changes to the model, it actually managed to recover from those setup differences rather quickly. And then we found that we could generate images which were a lot more realistic and a lot more variable, which is also what you want. You don't want it to just kind of generate one kind of image. You want to really capture all of the variability in your training data set. And this process actually allowed me to do that. So yeah, so a takeaway from that is that generative modeling is not really an exact science. I mean, the theory is well defined, but when you actually work with it in practice, you have to sometimes do some really crazy things to get it to work. So this is the encoder architecture of my variational autoencoder. So the input images were 17 by 24, so that gives you 408 pixels. So basically flattened each of those pixels out, and I just used a normal dense, fully connected neural network. I tried convolutional architectures, but I'll talk about why that didn't work. But essentially, I then have these various layers, each of which has like 512 nodes. And then after each node, I basically batch normalized all of the weights in that layer and then applied a leaky ReLU function. So leaky ReLU is similar to ReLU, where you think of like when the output of your summation node is 0, then or less than 0, then you give it 0, and if it's a positive number, then you just give the value. With the leaky ReLU, you have a bit of a gradient on the negative side, and that can also be trainable. So yeah, this is basically using leaky ReLU and batch normalization is just to kind of stabilize your neural networks. But essentially, after going through all these layers, you then map down to your actual Z variable here, and I used a latent space of size 5 or 5 latent dimensions. And then using this decoder architecture, I then mapped from those 5 latent variables back to my latent space. So, sorry, there wasn't enough space on the slide to just show the full network. So this is the first part of the network, and that's the second part of the network. But essentially, it's the same thing, just 512 nodes per layer. I don't know exactly how many layers, I think 6 or so. But yeah, so batch normalization and leaky ReLUs, and then you finally map back to your data space, and then you take that reconstruction loss to make sure that your generated data is as close as possible to the data that was fed into it. And this is what I found. This was the output of the Variational Autoencoder. So we still found quite a few of the images that were this sort of like inverted image, and they were quite easily distinguishable from true data. But yeah, we do find that the model quite often does confuse simulated data for real data, but we're still able to classify them quite well. So obviously this was a 1-year master's project, and if you were doing something like a PhD, you'd have a lot more time to really get and optimize these networks quite well. But again, yeah, we've got quite a bit of variability, so we don't get just one kind of image. We get some noise, so that happens in practice sometimes, where you either have a particle that went through here and another particle which went through there because your tracking wasn't 100%, or you can find something like this image over here, which is essentially a detector element that fired. So you can see that the total charge is never more than 20, and 200s or hundreds or so. So in this image over here, this was basically just detector noise, and even that is modeled by the Variational Autoencoder. And then I did a bit of a digging into the latent space. So these 3 plots are basically, I think the most important one is this one over here. So I found, I basically mapped, I simulated from everywhere in the latent space, but I set so I had 5 latent variables. I set the 3 later ones just to be equal to 0, so just to be somewhere in the middle. And then I plotted these 2 latent dimensions and tried to find areas of the latent space which resulted in highly realistic images being generated. So you've got kind of this little manifold over here where I found highly likely data being produced. And then these images were simulated from these areas, and they resulted in around 50-50 of being real. And then there was also another space which resulted in highly unlikely data points. So obviously, I mean, this is just the beginning of the investigation of the latent space, but it does give you a lot of value to be able to actually look at that latent space, which you don't really find in something like GANs, which I'll talk about in a bit. But yeah, so I then went and did this linear interpolation of this latent space, and basically the motivation behind this is that if you can actually understand that a particle that was traveling at, like, let's say, a momentum of 2 GeV, which hits a certain detector, would result in a certain type of image, you can then find where that, like, if you have the metadata, you can actually find where in your latent space does that particle map to. So that gives you a bit more control over what you want to simulate when this thing actually goes into production, into actual simulation at the LHC. But it's quite cool to see that if you move, like maybe in this space over here, you've got 2 particles that went through. If you move to certain areas in this latent space, you get completely empty images. And if you move, like, you can get some images which have like multiple peaks. So like you've got quite a couple of, like, for instance here, you've got 1, 2, or 3 peaks per image. So the red square was just the bounding box, was just to show that this is one simulated image. So I simulated images at each of these points in this latent space to kind of show where what mapped to. Cool. So like I said, visualizing the latent space is a promising investigation on how the latent space actually can be understood. Yeah, so I basically just explained all of this. But yeah, if you have sufficient data for each combination of possible features, then you should find specific areas of your latent space that actually produce those specific images. And then that would, if you want to then in production produce those kind of particles with those specific, like, measurables, then you can just give the specific latent encoding which maps to that, and then you can simulate that specific kind of particle, which is kind of what the Monte Carlo simulations do. And since your latent space is continuous, your inherent statistical fluctuations that are characteristic of physics measurements should also be captured if your latent space is exploited properly. So then you can generate unseen examples which could have possibly resulted from those particles with, so two particles with exactly the same measurable physical characteristics can actually result in more than one kind of signal being produced. And you can actually model those statistical fluctuations using something like a VAE. Cool. Then I looked at GANs. A lot of people think that GANs are really cool. I don't really respect them, but I find them fascinating. So basically what you do with a GAN is you can think of it sort of as a two-player game where you've got this art forger and this detective. And the art forger is sort of blind, and he's given some input like noise. And using that input noise, he's supposed to create something similar to an actual art piece. So let's take, for instance, the Mona Lisa. So what happens in practice is that you've got this discriminating neural network, which is given real data and data created by the generator. And this detective is supposed to tell the two types of data apart. So obviously the better the detective gets at telling true data and fake data apart, the better the generator needs to get at producing more realistic like images. So again, we're using two neural networks. We basically start, so we're variational autoencoders are going from big to small and then from small to big. We're basically going from a smaller representation to the data space, and this is just a random Gaussian, multivariate Gaussian. So from this random noise, we're actually we generate images. In the beginning, they're just random noise, and then we feed both the training, these generated images and the true data through the discriminator. The discriminator is supposed to tell these two types of data apart. So it's saying, is this a real image or a fake image? And then both networks are trained via backpropagation using this probability estimate of the data being real or fake. So essentially, this is, if you think about it in a game theoretic kind of approach, this is a two-player game, a mini-max game, where your generator is trying to minimize this function and your discriminator is trying to maximize it. So basically, the two terms here is like if you've got a true example X, you want your output of this final node to be 1. And if you've got a fake example, you actually want your output to be 0. So this is applying the discriminator to the output of the generator, right? So if you've got 0 in this term here, then you're maximizing this side of the function, and you're also maximizing this side of the function to a max of 1, of 2. And if your generator is winning, then all the two distributions apart, so it just outputs 0.5 everywhere. And this is shown in this image down here. So essentially, the static distribution at the bottom is your true data distribution. And the one that, okay, when it starts simulating again, you'll see that during training what happens is that, okay, it's just stabilizing. Cool. So you've got your simulated data distribution, and you've got this blue distribution, which is basically the output neuron, which is just distinguishing between the two of them. And then once your simulated data distribution is sufficiently similar to your actual data distribution, the output of your discriminator neural network is just 0.5 everywhere. So you've basically found like the saddle point of the loss function. You can't get lower than that. Cool. So the most successful GAN that I used had 4 latent dimensions. And basically what I did is I used 2 different optimizers for the discriminator and the generator. So you sometimes do stuff like that to basically just stabilize your neural network. You can also use like decay of your, like you can use learning rate decay if you wanted to, but essentially this also just stabilizes your GAN during training. Something else I did was I actually smoothed the labels of my true and simulated data. So if something is fake, I actually had, it could be anywhere between 0 and 0.29, and if it was real, it was anywhere between, the labels were anywhere between 0.71 and 0.121. So the reason we do this is that the generator, especially during early training, is never 100% certain of whether the data is real or fake. So because in the beginning the discriminator sort of like has an advantage. So we actually want to give the discriminator a bit of a handicap to not make it as good in the beginning, especially, so that it sometimes confuses true data with fake data. And then something I did was I injected a bit of prior into the bias layer of the output layer, so the bias term. So essentially, because most of the pixels in the images were close to 0, I added this bias term to have a mean of -2. And if anything, then if you sample this bias term and anything is below -2.2 or above 1.8, it's resampled until it's within that space. And I mean, I don't know if it's a mathematically sound thing to do, but it did actually work quite well in practice. Cool, and then these are the two networks that I used. So this is the generator. Again, we're mapping from this very small latent space through increasing number of layers or nodes per layer until we get just above 408, and then we map back down to 408, and we reshape it back to our actual image shape. And then the discriminator is fed this output of the GAN as well as true images, and it's tasked with actually telling the two of them apart. So for the discriminator, I actually use the convolutional network, not very intricate, three convolutional layers, and then I think almost like a similar, not even dense layers after that. So just flattening that convolutional output and then feeding that into a classifying layer. So yeah, so when generating things like human images, GANs actually perform quite well, but it didn't really perform that well in this task. So you can see that this classifying these two types of data it went quite well. So it was a lot easier for the convolutional network to tell GAN simulated data from true data apart from true data, as opposed to something like the Monte Carlo based simulations or VAEs. And also the data was very messy. So the images that produced they weren't very crisp. They were sort of like messy, but you still got some samples which was quite hard to distinguish from true data. So it did quite well as well. But yeah, still not my favorite setup. But so I used various types of GAN architecture. So there's various variations on that base concept. And they all gave results that appeared vastly different in terms of style. So if you use a different type of architecture, you get some very different outputs, but they all basically failed in the task. And GANs are really hard to train because you've got two neural networks pitted against each other. So if either one of them become dominant, they actually force the other one into a parameter space, which is not really conducive for either of them training well. And you sometimes get this thing in GANs, which is called mode collapse. So these are various images simulated at 21,400 epochs of training. And you can see that, yeah, they do all look like random noise, but you might start with the black line. So they all have these like similar features, but they're all kind of nonsense. So basically what happens with mode collapse is that only a certain number of modes of the true data distribution is captured by this GAN. But once you start seeing this, then you can just stop training the model. It's not going to recover from that. Then using convolutional architecture for both the generator and the discriminator actually gave very unrealistic results to me. So essentially, it's because convolutional layers introduced this prior that features are translationally invariant. So they can, if you think about like a classifying convolutional neural network, it doesn't matter if the cat is at the bottom or at the top of the screen. It's just the fact that there is a cat face that makes this a cat. So I think that this prior actually made the network think that it doesn't really matter exactly where these features are present, just as long as these features are present, it would actually say that, yeah, this looks like a true image. So yeah, and then sometimes during training, like in practice, you find that training after a certain number of epochs when you've got like an unstable model doesn't really improve your model. So you can see here, like after almost 100,000 epochs, you've got these outputs here. And training like 4 times more or 5 times more doesn't necessarily result in more realistic images. In fact, it actually started producing more unrealistic images after a while. So yeah, it's quite hard to train these things. Then this is something that I did only at the very end of my project. It's called Adversarial Autoencoders. So Adversarial Autoencoders basically combine both the concepts of VAEs and GANs. So you've got this small variational autoencoder setup where you map from your data distribution to your latent space and then decode that back to your simulated examples. But you also have this discriminating neural network, which it's not the same as the KLI versions, but it's quite similar. It basically says that you've got your negative examples which are your latent space variables, and then you've got this multivariate Gaussian, which you actually want your variables to map to. So these are your positive examples, and then you basically want to discriminate whether this latent vector is from the latent space or whether it's from your imposed prior, like what you actually want your distribution to look like. And that forces you to this is a proper enforcement of your latent space. So you're actually making meaningful examples come from everywhere in your latent space if you do something like this. So again, I trained with 2 different optimizers with 2 different learning rates, and I also employed label smoothing. And so this is just the architecture of the adversarial autoencoder. So you've got your encoding network, you've got your decoding network, and then you've got this network which is trying to distinguish whether the latent space is from the prior or from the latent space itself, so whether it's positive or negative examples in that case. And this really gave very, very nice results. I think this is a very promising avenue to explore further for people who want to actually work on this. Yeah, so you can see that there were quite a few latent or like simulated examples that were confused to be real. We still get a good separation, but obviously given more training time, given more training data, eventually you'll be able to, I think this is a realistic research avenue to explore. And you can see that you get in this, in your data distribution or your simulated distribution, you actually get things like, you can see that maybe there's a latent variable which determines at which point in this y-axis, which is your space dimension the particle went through, you get this fluctuation of energy deposit along the x-axis, and it's all modeled quite well. So yeah, I was quite happy with that. And like I said, the relative success of your adversarial autoencoders probably has a lot to do with the proper enforcement of the latent space. So you can generate meaningful examples from anywhere within your latent space. And yeah, I'm quite sad that I only got to these models quite late during my project, so I didn't get as much time to experiment with them as compared to VAEs and GANs, but I think that they're the most promising area for continued research. So yeah, so this leads us to the conclusions of my talk. So basically, building generative models I found is an extremely valuable tool to teach you how neural networks think, if that's anything you can really say. Don't want to humanize them too much, but essentially if you work with generative models, because you can sample output images at certain like intervals, like let's say after 10 epochs you sample a couple of images, you can actually see that if you change a certain parameter or you've changed your architecture in a certain way, you can actually see how that affects your output. So it teaches you a lot intuitively about how these networks work in practice. And it also shows that practical experience is really equally as valuable as theoretical knowledge, if not more valuable sometimes. So for my use case, I found that it was more practical to train locally than on a server because of that fact that you can actually simulate examples at certain in time intervals after certain epochs. So if you do that on a server, it wouldn't really be possible to do that in real time. Like you could simulate the images and then download them locally and then view them. But yeah, it's, you can actually, if you train locally, you can qualitatively assess how realistic the images appear based on your domain knowledge. And then you can just, if you see that the network isn't doing well, you can just force stop your training. Another thing to take into account is that if you use something like label smoothing and so on, you can't really use accuracy metrics and model loss metrics. You can't really understand them as well as you would if you did a classification or a regression model. Because you're doing label smoothing, you don't really know, like it's not realistic. Like if it says your loss is low, like it could just be because of that sampling process of the label smoothing. But yeah, so, and it's quite interesting that sometimes it can seem like your loss is quite high or that your loss is not reducing. So your loss just remains the same. But if you look at the output of your neural networks, of your simulated data, it actually is becoming more realistic. So both of, like in this case of a GAN, like both of them are actually becoming better. So the loss seems to be sort of similar, but they are actually increasing in accuracy. Yeah, so using different architectures and different hyperparameter settings can take different number of training rounds and so on before they actually start generating anything realistic. And sometimes models that seem promising early on in training actually get much worse later on. And another thing that was quite hard was that to load all 9.3 million tracks into memory is quite computationally expensive, as you can imagine. And obviously I was working on, I was doing my master's while I was working full-time, so you can't really just train generative models while you have to be at work. So you just have to make a trade-off and stop a model before it actually reaches its full potential. Yeah, and so just an outlook for future work. Like I mentioned, you basically, in order for this, for these generative models to actually fit within the existing simulation architecture, you need a well-defined API to actually simulate, to specify what you want to simulate. So basically, a particle with X momentum and Y particle type, traveling in a certain angle, going through a specific detector component, like where that maps to in your latent space, and where a different type of particle would map to. Then you obviously you don't use your encoder during training, so you basically just have this latent space which you feed through a decoder in production, and then you get your simulated data from that there. But you need to actually understand what you're going to simulate. You can't just like simulate randomly. And then another cool thing that another two use cases that could be fruitful, or avenues that could be fruitful, is basically using conditional GANs. So GANs are fed not only a latent space, but also a specific class that you want to generate. And so when you generate these fake images, the discriminator is tasked to actually say whether it's real or fake, but it's given both the data, like both the image and the class label. So it's trying to actually simulate specific kinds of images. So if you were like, let's cats and dogs, which everyone always uses, if you say like, here's my image and it's a cat, is this real or is this fake? Here's a real image and it is a cat, is it real or is it fake? So you actually get to specify what you want to simulate. And then you get this other setup called auxiliary classifier GANs, which is sort of similar, but basically the difference here is that your generator is given the Z variable condition upon the class, and then the discriminator is supposed to say whether the data is real or fake, but it's also supposed to say what class this image was from. Yeah, and then I've just got a couple of things that didn't work, but I don't know, are we looking for time? I think we're a bit over time, eh, Tambani?
Yeah, we're just a little bit over time there, just a tiny little bit.
Okay, cool. Yeah, so if anyone has any questions, I'll be welcome to discuss them. We can have a chat. So it's already important to show the rest of the stuff. So
yeah, Gerhard, I mean, thanks, man. Really appreciate the talk.
Thank you.
If anybody has any questions, please, this is the right time to sort of pop them through, and then we can sort of get into them.
Awesome.
I think everyone's a bit mesmerized by the talk at this point in time. Okay. Good. One question, comments? Lloyd says very interesting.
Oh wait, in the chat, eh?
Yeah, in the chat.
Awesome.
Anything.
Thanks, guys. Yeah, I suppose if you want to talk about it afterwards, message me on LinkedIn, and I'll make the slides available to you guys on the Meetup link.
Sure.
Thank you for listening in.
Yeah, so if you don't mind, what we did with Albert for his talk is we just set up an AMA on our Slack channel. So we've got a Slack channel on CTML on Slack.com. And so we can just set it up there. So we'll just add the slides, and we'll also just talk on YouTube as well on the Data Chief channel. So if anybody wants to watch it after the fact, they can do that. If they want to ask questions, then they can just like Slack you for about a week. So we'll just set up that channel for a week and then we'll sort of shut it down. We have a question from Keith, and Keith is saying, what motivated the use of the leaky ReLU relative to the standard ReLU?
So there's this website, there's actually this Git repository called GAN hacks, and this is like, because there have been so many people that have actually tried to make GANs more successful, they've actually employed various different strategies. The leaky ReLU, I'm not 100% sure why it works, but it's just one of the suggested methods to actually make your training process more stable. It might have stronger gradients, I suppose, than a normal ReLU. But yeah, there's actually, I'll also maybe add the link to that repository. There's also some other repositories that I can link to that give you some sort of like a starter network that you can start working with if you want to just try it out on some data on Kaggle or something. But yeah, it's just a suggested method. Same as batch normalization, it just increases.
Thank you. So there's another question from Jethro. He's saying, how do you manage your time working and doing masters at the same time?
Short answer, I didn't. So,
I think the answer for everyone. Like, it sort of happened by mistake, you know. Kind of stumbled through it.
I got a lot of study leave, so 22/7 did give me about 18 days of study leave, which if I didn't have that, I would have never been able to do this. But yeah, I slept very little, and I just kind of used my weekends and after work and sometimes before work. Yeah, so it's tough, man, but like I really think that it's worthwhile. So if you're thinking of doing a master's and working, like give it a shot, you know, you don't know how strong you are until you actually do it. So yeah.
I also think like sort of as you I think the first sort of the first bit of your masters is kind of you're kind of figuring out like what the topic is and like what you're going to do and like you're kind of figuring out like, what's going on.
Yeah.
I think you accelerate through a bit. I think you become more efficient near the end than you were at the beginning.
Yes.
That's We're getting another question from Georgina, and she's saying, how much of this kind of work do you get to use at 22/7?
Georgina, as you can imagine, Georgina also works at 22/7, so she's sort of like one of the foundations for the data space there. But not a lot there. I work with more. We do actually. You might be interested to know that we've put machine learning into production for the first time in 22/7's history. So we've actually extended the classification of your transactions using XGBoost. So we have put some machine learning models into production, but obviously, I suppose we might be able to use something like net worth prediction or something like that with neural networks, but yeah, not really GANs or VAEs or anything like that. But obviously knowing the more advanced techniques makes you a better data scientist in general. So
so I think it's tricky. So like I guess most teams will never really find much use, especially if you want to do quote unquote explainable AI. Probably won't find much use for sort of like deep neural nets, especially stuff like generative adversarial networks, et cetera. But that it also depends on the kind of problems that you're facing, right?
Sure.
I think this use case that you have where you're sort of learning an underlying data distribution from a latent space so that you can interrogate the latent space about the data and so that you can essentially generate results for simulations that didn't exist. That concept is a very powerful concept. And I think that's actually a very sort of good practical use of these kind of latent space models. And it's probably going to find serious commercial applications somewhere along the line. You could probably imagine things like what do you call it, like fraud, right? Like anomaly detection. If you can understand the underlying space really, really well, you can actually create new anomalies and investigate what they look like, and actually be able to identify those events. But that's just like sort of spitballing.
No, 100%.
Has a follow-up, and he's saying that he's done his honors in computer science, and he doesn't do a lot of math and stats. So he's wondering if it's necessary for him to pick up sort of second year and third year stats first before he gets into this kind of work in the data science space.
Look, I think it's useful. They'll also give you like sort of like a crash course in statistics when you join. So you're expected to know your first year stats quite well when you start your masters. But it's sort of like a 2-week period where you get a crash course in second year statistics. I myself had only had first year stats because of my my training in biology instead of engineering or math. But yeah, so you do get a crash course. It's hectic. You also get at the same time the practical side where you do Monte Carlo in R, and you get an introduction to R in general. So I wouldn't say that you should limit yourself. I think there's technical debt that you'll have to pay at some point. So I'm paying a lot of that technical debt now. Like I'm doing a lot of reading of stats and math just to get myself on. I think as long as you can code, as long as you've got some understanding of data, like the course is to actually teach you this stuff. So yeah, don't be too scared of not having the background. Like,
yeah.
Georgina, no. I worked in R for about a year, after 2 years after my master's, but I've moved on to Python. I think it's just a sensible thing to do. Use production, like R is not the way to do it.
That's not true, man. It's true. You can't use it production. It's just a lot of work.
Yeah, it is, and no one else knows how to use it. So you'll be the only guy working in R.
Nobody can tell you that your model is wrong.
Sure. if that's what you want there. But yeah, no. I actually used to think R was better for data wrangling with dplyr and so on, but Pandas is quite good at that stuff as well. There, there's some nice stuff in the Pandas as well. So, yeah.
Yeah, we still use R. We still use like, well, I haven't used R for like any quote-unquote data science for a while, but R is great for like writing technical reports. Like I have to say, like it's like really fantastic. Like the R Markdown and that book down. If you want to write something that's really, really nice, like a really nice technical report, it's just a way to go. And of course, you can still actually analyze a bit of data in there. So if you have like logs from your models, you can then generate like all your graphics and whatever, Markdown and your later. It's a really nice way to go.
That's true.
And of course, the RStudio IDE is also like incredible. I think it's the best data science IDEs that's out there, especially if you compare it to those Jupyter notebooks.
Yeah,
I'm not a massive fan of.
No, it's true, because you can always, like with your variable explorer, you can actually just view the data instead of like printing the head of your data in like a Jupyter notebook. But that never gets formatted faster. You can't scroll through it. It's just
it's just not ideal. Like that's actually the interesting thing. Like when I was using RStudio, I never printed my data.
Yeah, exactly.
You just never need to do that. You can see how much memory your data is taking. So before you even do something, you see that you've got like 8 gigs of data in memory, and you immediately realize I need to do something. When your Panda is like you're in the dark, and it's just it's not ideal.
Pandas greatly attributed. Use Dask.
Yeah, or Spark.
Yeah, exactly.
Yeah, I think we've reached the end of our questions. Gerhard, thank you, man. Thank you for the talk.
Thank you.
Thanks for recording. Like I said, we'll set up a channel on the Slack, and then people can sort of ask you whatever's outstanding, and then we'll send you YouTube for anyone who didn't catch it. I guess that'll be the end of that.
Perfect. Thanks everyone for listening in. I really appreciate it. Awesome. I hope you found it interesting.